Welcome everyone. For today's prep, we're going to see how substitution rule works if we're trying to calculate a definite integral. And the thing that's really going to be new here is how we handle the limits of integration. And there's kind of two methods we can use to really deal with those limits of integration. And the first method, the method we're going to look at in this prep video, is to actually change the limits of integration from the original variable, which in the case of the example we're going to do is x, and we're going to switch them over to our new variable u. So the benefit of this approach is that when we go through the integration, normally with a substitution rule problem, we have to convert our antiderivative back to x. So the nice thing about this method is we won't have to. So let's see how this works. The other method, real quick, we'll try an example like this in class, is to not really do anything with the limits of integration. Just leave them in terms of x, and then get your antiderivative back to the original variable, and then evaluate from there. So we're going to see kind of a method one in the example we're going to look at. So we're just looking at one example here. We have a definite integral. The function we're integrating is 2x times x squared plus 1 raised to the power 5. And the limits of integration here are 0 and 1. So we're looking at the kind of the section of the x-axis going from 0 to 1. Okay, so how does this start off? Well, we're going to start it off just like a regular substitution rule problem. So first step, we want to think about what should we choose for u, and we want to calculate du then, once we have our pick for u. All right, so again, when we're trying to decide how do we choose u, we're looking for the inner function really. And if you see parentheses, usually a good first guess, if you're not sure, is the stuff inside the parentheses. So that's what we're going to do. We're going to let u equal x squared plus 1. Okay? So this x squared plus 1 here, we know we're going to switch that over to u. Then we want to look at all the other stuff that we have left over. So we have this 2x, and then we have this dx. We calculate our differential. So forget about the integral for a second. So forget about all that, and just do the derivative of what you picked for u. So our derivative here is just going to be 2x, and then to get the differential, we multiply that by dx. All right, so now we compare. What do we have in our differential that matches up with the leftover terms in our integral? And we see that in this case, we kind of get lucky, and everything matches up perfectly. We have the 2x, and that's 2x is in our differential, and then we have this dx matches up there. So everything matches up perfectly here. So we're going to be able to replace that 2x dx with our new differential du. All right, so let's start. So normally the next step is substitution. So we want to substitute everything in. So let's do that. And I'm going to leave my limits of integration off right now. So we're actually going to switch those over. All right, so what happens? Well, that x squared plus 1, or the x squared plus 1 raised to the power 5 becomes u raised to the power 5. So we're just switching that over with our substitution here. And then the 2x and the dx get swallowed up, and they become part of our new differential du. Okay. So this is kind of standard u substitution so far. All right, so now what's going to be new is these limits of integration. So we're also going to substitute these. All right, so how does this work? Well, let's write our limits of integration down. So we have x equals 1 and x equals 0. And when you do this, it helps to kind of keep them in the same order that they appear. So x equals 1 is our upper limit, x equals 0 is our lower limit. And the idea is we're going to take these two x values and we're going to plug them in to our u equation. So we're going to plug these into u equals x squared plus 1. All right, so what happens? Let's take x equals 1, plug it into here. So that's going to give us u equals 1 squared plus 1, which is 2. And then if we take x equals 0 and plug it into our choice for u, we're going to get u equals 0 squared plus 1, which is equal to 1. So these are going to be our new limits of integration. And when you do this, you just want to be careful that you match them up correctly. So x equals 1 gave us u equals 2. X equals 1 was our upper limit, so that means 2 is going to be our upper limit. And for x equals 0, we got u equal to 1. Well, x equals 0 was our lower limit, so that means u equals 1 is going to be our lower limit. All right. So now we've substituted all the pieces in. We had to do this little bit of extra work to see how our limits of integration switch. So now this just becomes a regular definite integral where it's now completely in terms of u. So now we just evaluate like regular. So we find the antiderivative. Do a little power rule there. And because we're doing a definite integral, we put the vertical line, which means evaluate, at the end of our antiderivative. And we put our upper and lower limits on the kind of the ends of that vertical line. And once we have our antiderivative, now we're ready to evaluate. So that's the last step here. So the way we do this evaluation, we take the top number, plug it in. So we get 1 over 6 times 2 raised to the power 6. Then we subtract, and we plug the lower bound in. So we get 1 over 6 times 1 raised to the power 6. And again, for more complicated ones, usually it's a good idea. Kind of set up the framework for the evaluation. So big set of parentheses for what you get when you plug the top number in, big set of parentheses for what you get when you plug the lower bound in, and then the minus sign in between. So that's our last step. Do the evaluation. And for definite integrals, we could simplify this down. Perfectly fine, though, to just leave it like that. Although 1 to the power 6, you could probably simplify. All right, so this is the idea for substitution with definite integrals. So really the only thing new here, basically it's the similar steps as what we've been doing for indefinite integrals. The only thing different here is just we also have to now switch over our limits of integration. All right, so we'll get a little more practice of this in class, so we'll see you then. Bye-bye.